All right, so 5 more problems and we'll be done with this homework lecture, which was already 2 hours long, the first part. So, uh, all right, so thin conducting plate, 1 meter on a side is given some charge. So a plate of metal, big plate of metal, a meter on each side. That's this big, a yard, 39 inches by 39 inches in the English system. A little change. Electron is placed. Good luck picking one up all by yourself. 1 centimeter above the center of the plate. What's the acceleration of the electron? So if the plate is charged negatively, then an electron will want to go away from the plate. So we know that much. So the thing that you don't know, and this isn't in your book, but I want you to know it, is that there is the electric. So we have a plate. Just kind of draw one here. Um, so this is 1 meter, 1 meter, and it has that minus charge. And then there's an electron that we would put above this plate. Okay, that's 1 centimeter above it. It's an extremely large electron. Okay. It's going to want to zoom away since that's a negative charge. So we know that it's going to get pushed that way. And there is a formula. So for a plate, a thin conducting plate that's charged, there is uh, we know the charge density. Now it's an area density. So there's 3 kinds of density that you can have. You're used to volume density, okay, from chemistry. Mass per unit volume, which would be some sort of side cubed thing. But you can have an area density, how much is packed into this flat space, okay? And you can have a linear density, like imagine if you had a tube of, gumballs, you just stack one on the other. There would be a linear density, how many gumballs per inch or foot or whatever. Okay, so we can have density doesn't have to be strictly a volume thing, all right? And there will be a density because only so many charges will fit on that plate. And since they all distribute evenly, since it's a uniform shape, then I can know that there's a uniform charge density, and it could be computed. So we're given it, all right, here, and so we have this symbol for. We like to use sigma, but just know that this is uh, charge density. And since it's a square meter, we already know that it's -2 times 10 to the minus 6 coulombs per square meter because we're dealing with a square meter. All right, easy peasy to figure out the linear charge density. If it wasn't a square meter, we'd have to divide it by its actual area in meters, and then we would have some other charge density than -2. But this one was picked for this reason. We could just easily make our linear charge density. And there is a formula when you have a shape like this. So this is definitely something to put in your post-lecture bullet point notes, the kind of things you'd put on a formula card. When you have a plate, a shape of this type, uh, it is the charge density over 2 times epsilon naught. Now we've only mentioned epsilon naught once. It's buried in the Coulomb constant. It's part of it. All right. And so this, again, this is the electric field of a uh, charged plate. So this is just a plug and chug. Now, epsilon naught has a value, and it's 8.85 times 10 to the minus 12. And I'm going to have to verify that because my brain is making me doubt that I remember that. I know it's 8.85, and I'm almost certain it's 10 to the minus 12. We'll find out later whether it is or not. Okay. What is epsilon naught? Good question. I'm glad you asked. It is the permittivity of free space. It's the electric permittivity of vacuum. So outer space or anything that's got nothing in it, basically. And there's an electric permittivity of space, and there's a magnetic permeability of free space. We'll get to that in later chapters. And in fact, the speed of light is uh, known because of those two factors. The product of the square root of those, the factor of those two products under inverted is what the speed of light is. Now, Maxwell figured that out. We'll see a movie next week about that. Um, but it's buried in that Coulomb constant. So free space, it's not like, electric fields and magnetic fields can't go infinitely fast. In fact, every field effect is limited by the speed of light. It can't transmit that force any faster than the speed of light. So, for instance, the gravity, it takes 8 minutes for the gravity of the sun, as it is right now, to influence us on Earth. Okay? Takes light 8 minutes to get to Earth. And so, like, if I were God and I could just instantly remove the sun from this solar system, it would take 8 minutes for Earth to fly off of its orbit, because Earth wouldn't realize that the sun is gone for 8 minutes. We'd keep seeing the sun and feeling the effect of its gravity for 8 minutes. And then suddenly it would get very dark and very cold. And then we would be flying off along a straight line out of the solar system. Of course, there wouldn't be a solar system anymore. There was no solar part to it. And so all field forces are limited by that. Okay. And the closer you get to the speed of light, the harder it is to add more energy, momentum to the system. All right. But permittivity of free space, there's some sort of limit on how fast and how much electricity or electric fields can go through space. Same with magnetic fields. So I have a number, it's a constant, and it was derived in a similar fashion to the way we've derived other constants. A bit more complicated, but functionally the same basic idea that we've done even in this class. All right, little side street on electric permittivity of free space. You can read about it, Google it, et cetera, et cetera. All right, so it's that number, hopefully the right exponent on it. And if we do the crunching of all of this, we'll get 1.13 times 10 to the fifth newtons per coulomb. And remember, if each of these problems serve as nice ways to keep reinforcing ideas, and these are abstract ideas. The concept of an electric field is an abstract idea, okay? And I've told you that every field effect, every field force, gravity, electricity, magnetism, are always the force associated with that field, in this case an electric force, per unit, whatever is the source of that field, which is charge in this case, and we measure charge in coulombs. So, 1.13 times 10 to the fifth newtons per coulomb, units of force per units of charge. If you remember from last semester, little g, it's actually not helpful to call it the acceleration due to gravity, even though it is that, in reality, but it's technically the field strength, the gravitational field strength of Earth. And so I can understand little g is 9.8 meters per second squared, but really what it is 9.8 newtons per kilogram. So you throw something up in the air, and as long as it's in free fall, which includes the moving up, because if it's under the influence of gravity, it's in free fall, okay? Uh, if it's moving, and so 9.8 newtons, there's a 9.8 Newton force, okay, pushing down on every kilogram of that object that got thrown. 9.8 newtons per kilogram. Same idea for electricity, except it's a different field force. And it's a field force that exists because of some other charges in the universe. All right. So just a reminder there, it's been a whole week since we talked about electricity. So I know that it's easy to let those ideas slip. So that's part A of this problem, that we have the electric field, but the question is, what's the acceleration of the electron? Well, Newton's second law, F equals ma. So I have the electric field, but what I need is the force that's on it. Okay, I know the mass of an electron, it's a known quantity that we'll look up. Be great if there was a webcam on my video thing so they could see us doing the wave every time the lights go off in this room. It's nuts. All right, so we need to compute the force. So electric field is defined as force per unit charge, which, wait a minute, charge is a Q, not a G, all right? Which means that this electric force is just charge times electric field. So that means the force that we're working with will be the charge of an electron, which is 1.602 times 10 to the minus 19 coulombs, times the field that we just computed. And that will work out to 1.86 times 10 to the minus 14 newtons. So that's basically 100, almost 200 trillionths of a newton, which isn't much force, but it's a lot of force if you're as small as an electron. And then finally, so Newton's second law, acceleration is force per unit mass. So we'll have our 1.86 times 10 to the minus 14. The mass of an electron, which we've used a couple times already, but you could look up, 9.11 times 10 to the minus 31 kilograms. And again, now you can see that acceleration in this case is going to be newtons per kilogram. That's a more proper way to talk about it, but it just does happen to work out that newtons per kilogram from a unit standpoint is meters per second squared, or meters per second every second. So now we crunch and munch here, 2.04 times 10 to the 16th meters per second squared, which is what you'll see in a textbook, but know that that's meters per second. All right, meters per second every second. Well, obviously, that's like the speed of light squared, okay? An electron is not going to obtain that speed anywhere, okay? It's physically impossible for an electron to obtain that speed, but that's the force it's under. And I would suggest that this is a moment here. And so if you're note taking, you might say, go back to 14 minutes in this lecture and think about what Van Gilder is saying right now. Okay. When you look at this, an important fundamental understanding to take away from this result is knowing that nothing can exceed the speed of light, which means in less than a second, this thing would if nothing kept it from doing that. Okay? And so here's where all the math is correct. We have obtained the speed of light squared, basically, because speed of light's 3 times 10 to the 8. And so this is slightly less than the speed of light squared. Okay, 10 to the 8 squared would be 10 to the 16th meters per second every second. And that's why it's technically better to think of this as newtons per kilogram, all right, um, because it sort of, that I can understand. A lot of force per unit mass. That's undeniably true. That's the force that this thing is under. Now, if I also, in parallel to what is fundamentally true about how much force per unit mass is on this thing, which is a crazy, insane amount of force per unit mass, if I interpreted that in terms of motion, I wouldn't want to make the mistake of thinking that it could actually obtain that speed in any number of seconds. Okay? Next thing to think about is, well, okay, this is yet another example, and it's a drum I'm going to beat throughout the course of, dang, there's a lot of energy packed in these electric fields. There's so much energy in there that, if there wasn't a limit on the speed of an object, this is insane. That's like warp a million. If you think science fiction, that's just really nuts. All right. You could get to another galaxy in a few minutes, if you could go that speed. So just ponder that. So at 14 minutes into this lecture, there's something that is notable for your learning outcome essay. You want to kind of go, you don't want to just give a journalist, scientific journalism of we did this, we did that, I heard this, I heard that. You want to try to run with it somewhere, see what it means and ponder those ideas. So there you go. No extra charge on that. So the question's been answered. That's the acceleration that it gets. What I didn't specify, was how to understand it. Like your homework just wants the acceleration, and it doesn't prefer newtons per kilogram over meters per second squared, because I never ask you for the units, because that just makes it the grader. If you type it in wrong, Blackboard's, computers are stupid, people are smart. Computers do exactly what they're told, people don't, unfortunately. All right, on the next problem. Calculate the magnitude and direction of the electric field 2 meters from a long wire that is charged uniformly at a linear charge density, lambda, of 4 times 10 to the minus 6 coulombs per meter. So a long wire. So here we have a long wire. All right. And there is a formula. So I'll put long wire. And so the electric field for something like this is going to be the Coulomb constant K times double the charge density per unit length. So where does this formula come from? It comes from doing calculus, which we don't do in this course. And again, you won't find this in your book, at least you shouldn't. But I think it's simple enough, given this formula and trusting that it's a legitimate formula, we can think our way through this. So, by the way, just so you know, K, and this is in your book, is 1 over 4 pi and that epsilon naught thing. So if you wanted, you could solve this equation for the little K equation. K is 9 times 10 to the ninth. You could solve it for epsilon naught and verify whether or not I had the number right on the other screen. But just a reminder that that's what K is. Said it a couple of times, but worth noting. All right. So if we put the numbers in here, because we have everything that we need, the charge density was 4 times 10 to the minus 6 coulombs per meter, and the distance was 2 meters away. And so the electric field going away from this thing would be 3.6 times 10 to the fourth newtons per coulomb, and it's going to be up along the y-axis. If we wanted to, I don't think your book, forget whether or not it deals with vectors, but you would have a k hat, not to be confused with the k constant in Coulomb's law, okay? But it's going up. So as long as we specify up, that's all that really matters, okay? It's pushing away from that rod. Now, in reality, let me redraw the rod down here. What you have is, if this is a charged rod, let's just say that since it was a positive charge, you know, we have all of these plus charges, which are really just the positive cores that are exposed. So this is also something we talked about at some length on the first day. Electrons, excess electrons, have been stripped from this rod such that the positive cores are more dominant along the surface of that stick. It's not like you can actually add protons to something. Well, you could, it would just, now it's not that something anymore, okay? And so we lost some charge, some negative charge, therefore it's more positive, it's a net positive. And one of the things we learned last week was that electric fields emanate from positive charges and terminate somewhere on a negative charge. So electric fields are pushing out from positive charges, electric fields are pulling in on negative charges, okay? So that's that for that problem. Simple formula, but also not in your book. But I want you to know these things. They should have put it in your book. All right, but they didn't. 2 thin conducting plates, each 25 centimeters on a side, are situated parallel to one another and 5 millimeters apart. So we would have 2 plates, and I'm going to exaggerate the distance, okay? So let's see here. This is supposed to be 5 millimeters, and these plates are 25 centimeters on a side. So we won't bother with the other dimension. We'll just look at them straight on side. Basically, this is a capacitor. We'll have a whole chapter devoted to capacitors. And I've told you before, capacitors are basically electronic shock absorbers. They have the ability to take a big surge of current, which is a bunch of charges moving, and then there's this pause while it discharges across the plates, so to speak. It doesn't actually move from one plate to the next, but the charge is transferred through that medium, whatever's between them, air or otherwise. And so, but we'll get more to that later, but just have this thing here. So 2 thin plates, 25 meters aside, 5 millimeters apart. If 10 to the minus 11th electrons are moved from one plate to another, what are we dealing with? So the area charge density, we're dealing with an area. So this is like the single thin plate we had in a previous problem, all right? So we need to figure out charge density so that because we're going to use this formula again. The electric field, when you have a thin plate, is the area charge density per epsilon naught. Previously, it was 2 epsilon naught, but we have 2 plates. So we have double the density, so that's why the 2 drops out, okay? So first we got to figure out the charge density. Well, every electron is 1.602 times 10 to the minus 19 coulombs. Okay? And we have 10 to the 11th. That should be, I need to erase that minus there. Okay, so this, it should be 10 to the 11th, not 10 to the minus 11th. So be mindful of that. You can't move 1/10 trillionth of an electron. You moving 10 to the 11th electrons. What's the electric field between the plates? All right, so next thing is that was over epsilon naught. But the distance, well, charge density, so let me write here. So we have 0.25 meters squared. So where am I getting this? Well, I don't have a formula. I have what an area density would have to be. It would be how many things are in the area per unit area. All right, so this is number of things per unit area. Okay, so it's a conceptual formula. It's not like you're just going to find it. It's the way you would define area density. Any density is always some number of some things per unit length, area, or volume. Okay, in this case, it's area. So our charge density, or the area charge density, is going to be 2.56 times 10 to the minus 7 coulombs per meter squared. Last time we had a charge density, we didn't have to think because it was already in a square meter. Here, it wasn't in a square meter. It's in a square quarter meter. All right. So now we have that linear charge density, which means we can put it in our formula, our handy dandy formula, over epsilon naught. And when we crunch that, we get 2.9 times 10 to the fourth newtons per coulomb, which is a lot of force. So 10 to the fourth is 10,000. Okay, so like think of your weight, or you can think of my weight. Okay, so I'm basically 100 kilograms, or I'm 100 I'm 100 kilograms, which means I'm 980 newtons of weight force. So 200 plus pounds would be roughly 1,000 newtons. Okay, and this is 10 times my weight. This is double, I'm sorry, almost triple of 10 times my weight. All right, so if 30 of me were standing on you, you would notice that. Okay, but this is individual charges feeling this much force per coulomb. All right, that's a lot of force per coulomb. All right, so you always want to think through what would this number mean, and you'd have to put it in context of something else that you can relate to. All right, so my weight is probably average or maybe above average for men. Maybe it's average for people in general. I don't know. I would suspect it's certainly not below average, unfortunately. Okay, I'd love to be below average on that one. That would be nice, but life throws its curves. All right, quite literally in that case. But boom. All right, moving on. An electron and a proton, each starting from rest, are accelerated by the same uniform electric field of 200 newtons per coulomb. Determine the distance and time for each particle to acquire a kinetic energy of that amount, 10 to the minus 16 joules. All right, so key idea here in reading this is we were told that we have kinetic energy, all right? And so hopefully you remember that kinetic energy is 1/2 mv squared. That's sort of basic knowledge for Physics 1, and we're in Physics 2, so you're supposed to remember that for the rest of your life. If you didn't, you have a second chance to commit this to memory. Get a tattoo or something. All right, so that means that it's going to be, since I know the kinetic energy amount that we're given it, 3.2 times 10 to the minus 16th joules, and I know that that equals 1/2 mv squared, and I am dealing with an electron and a proton which have known masses, that means I can find the speeds of these two particles, which are going to be different because they have different masses, but same energy uh, that they're dealing with. So the speed, well, let's do this first. Let's solve it for v. So this means that v squared is going to be 2k over m, which means in general, v will be the square root of double the kinetic energy over the mass. That's going to be our general formula in this case. So electron. So the speed of the electron will be the square root of 2 times, and I'll put this 3.2 times 10 to the minus 16 joules. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms. And again, crunch and munch on that, and you get 2.65 times 10 to the 7th meters per second. Now this is actually a pretty good, this is a realistic speed. It's 10 times less than the speed of light. Speed of light is 3 times 10 to the 8th meters per second. So this is feasible for an electron. At the Large Hadron Collider in Geneva, I think it's Geneva, somewhere in Switzerland, they can get protons up to just under 3 meters per second of the speed of light, almost to the speed of light. It takes an enormous amount of energy. Basically, a big magnetic track, big magnetic tube keeps them inside of the tube on a circular path, and then there's these electric field slappers. You know, as it moves through this electric field, it gets accelerated, and they keep doing that all the way around, and eventually it gets up to the back speed, and then you actually have two particles going opposite directions on different circular paths, and then they flip a switch so that those paths coincide, and then they have detectors in that spot, and they take a few months to analyze the data. There'll be like 100 people working on the data from just that, and it takes them months. So checking, double checking, you know, it's quite a process. All right, so that's the speed of the electron, which means the acceleration of that electron, okay, will be so if we have where would we get the acceleration formula? Any ideas? Anybody remembering the zeroth law theorem? All right, v squared equals what? Anybody remember? 2a ds. We don't know the distance, so this is going to be, we can't go that route. We can't go kinematics. What we can do, we know that acceleration equals force per unit mass. We know that the force is going to be the charge times the electric field. That's the way force is defined. In this case, the charge is an elementary charge unit. The electric field's given up here in the problem, and the mass of that electron is known. So 1.602 times 10 to the minus 19 coulombs times 200 newtons per coulomb over the mass of an electron. And the acceleration will be 3.51 times 10 to the 13 meters per second squared. Again, it's not going to obtain that speed in any number of seconds, but that's what the acceleration is at that moment. All right, so that's the electron. Proton will be the same maneuver, okay, except you're going to have the mass of a proton. So to 3.2 times 10 to the minus 16 joules, a proton is 1.67 times 10 to the minus 27 kilograms. And that means we're going to get a speed of 6.19 times 10 to the fifth meters per second. And if we go through the same rigmarole for acceleration, above we'll get 1.92 times 10 to the 10th meters per second. Last problem. Require us to do a little geometry here. So a spherical droplet of water of that radius, so 25 micrometers, that's 25 millionths of a meter, okay? So take a millimeter on a meter stick, divide it by 1,000, 25 of those little increments is what 25 micrometers is. What vertical electric field is needed to balance the gravitational force? So let's zero in on something here. What vertical electric field is needed to balance the gravitational force? What that means is that the electric force must equal the gravitational force. So the interpretation, the thing that I would want you to see or be able to believe, is that that sentence, when it says what vertical electric field is needed to balance the gravitational force, that means if they're in balance, that means the electric force would have to be the same size as the gravitational force. They're in balance, that's where the equal comes from. So balance, that's why they're equal. So electric field, gravitational force, in balance. That's what I would want you to catch from this problem. All right, so electric field. Well, the electric field, or the force of the electric field would be the charge times the electric field. That's just applying the definition we've gone over a few times. And then mg, that's the force due to gravity. So requiring you to remember that gravitational force, or the weight force, is mg. And then we're requiring you to remember what we've recently defined as the electric field, which is force per unit charge, or if you flatten it with no fraction, you have force equals charge times electric field. So think about it. Force is force. And charge and mass are the things that operate under those two different fields. And we explicitly call capital E the electric field, but we tend to not call little g the gravitational field strength. Little g is the gravitational field strength, mass times the gravitational field strength. Big E is the electric field strength, charge times the electric field strength. it's a we have this unfortunate thing that all the textbooks tend to not emphasize that little g is a gravitational field strength. Um, Not just why we did that, I don't know, but it's worth repeating conceptually. So now, basically, I have everything that I need to know in the problem except uh, mass, which I'm going to have to do some geometry thing by virtue of volume. I wasn't given mass, but I was given volume, or I was given a measure for a sphere, and I know the volume of a sphere is 4/3 pi r cubed, all right? And then the mass would be the density times that, uh, or I could rewrite mass as density times volume. So let's get to this. The first thing we need to do is figure out the mass. So the mass of this sphere, okay, is going to be density of water is 1,000 kilograms per cubic meter. Okay, so that's density. So remember, mass will be density times volume. Hopefully you remember that from chemistry. Now the volume here, I know that the volume of a cube, or I'm sorry, of a sphere is 4/3 pi r cubed, and our r is this 25 times 10 to the minus 6 meters. That has to get cubed. Okay, so I have density of water, volume of sphere, or spherical drop, if you will, in this case. So if we compute that, let's see, what does that crunch out to be? So 6.5 times 10 to the minus 11th kilograms. So now I know what that needs to be. So we wanted to know what vertical electric field is necessary. So that means I solve this for E, which is going to be mg per q. So my m is what we just found. G, little g hasn't changed, it's still 9.8. I'm going to put newtons per kilogram. And then the charge was 250 times the elementary unit of charge, which is 1.602 times 10 to the minus 19 coulombs. So that means our electric field will be 1.6 times 10 to the 7th newtons per coulomb. So that's 16 million newtons per unit charge, or per coulomb, rather. That's a lot of newtons. That's a lot of professors standing on top of this pile of electrons. And that's it.